So if I want to write this matrix in this basis, I need a change of basis matrix. I'm going to use matrix P. Its columns are going to be the eigenvectors here, my new basis. So I'll have 3, 4, 1, -1, and that's in the EB. Okay? It changes me from basis B to basis E, from my new basis to the default basis. Now remember, in order to change the basis for a matrix, you have to hit it on both sides. You have to transform the rows and you have to transform the columns. All right? So we do P inverse AP. P inverse 1 over the determinant, swap, negate. Just like that. I'm going to put the minus sign inside. Just like that. And now all I have to do is work out this matrix multiplication. So I would have 1 plus 4 is 5. 3 plus 2 is 5. 4 minus 12 is -8. 12 minus 6 is 6. This would be BE again. 3, 4, 1, -1. EB, 1/7. All right, let's see what we got. 15 plus 20. 5 minus 5. -24 plus 24. -8 minus 6. I have my overall factor of 1/7, but the diagonal elements are divisible by 7. So my P inverse AP which I'm going to call matrix D, is 5, 0, 0, -2. Now, what is the significance of the numbers that appear on my matrix D's diagonal? They're the eigenvalues. That's right. They're also in the order that we chose to put the eigenvectors. This eigenvector was chosen to go first, and therefore the associated eigenvalue is the one that goes first. Had I instead used 1, -1, 3, 4, I would still get a diagonal matrix, but it would be -2, 0, 0, 5. All right? Now, what are the chances that this was just an accident? Zero is the chance that this is just an accident. Let's look at what these vectors look like in the B basis. They're just 1, 0, 0, 1. Matrix A, when acting on this vector, has to give 5 times that vector. Matrix A, when acting on that vector, has to give -2 times that vector. So that means in the B basis, matrix A has no choice but to be represented by this diagonal matrix. This process of changing a matrix to its own eigenbasis is called diagonalization. We took matrix A and we found a similar matrix, matrix D, related to matrix A, a change of basis, otherwise known as a similarity transformation. All right? So we diagonalized matrix A through a similarity transformation. Now, there are 2 invariants for similarity transformations that we discussed: the determinant and the trace. So let's check. The determinant of matrix A is 2 minus 12, which is 10. And that's also the determinant of matrix D, 5 times -2. The other invariant under similarity transformations was the trace. The trace of matrix A is 3. And the trace of matrix D is also 3. All right, these are not accidental, because as we saw before, determinant and trace are always invariant under a similarity transformation.